Okay, so this is 5.2, exploring quotients and polynomial functions. Okay, so we're going to look at different rational functions. Okay, so those rational being fractions. Okay, so we're going to look at a bunch of functions that are in fractions. That could be expressed as p of x over q of x. I'll explain what this is later with examples. P of x and qx are polynomial functions, but q and x cannot equal 0 because we can have a 0 in the denominator. Many discontinuities can occur when dividing polynomial functions. Okay, so the first one. Okay, so a rational function f of x equals p of x or qx has a vertical asymptote at x equals a if p at a over q at a equals a p a over 0. Okay, so an example. Where's my markers? Okay, for instance, so if I had said, say, some x plus 1 over x minus 2, for instance. Okay, so we're going to have a vertical asymptote where our denominator is equal to 0. Okay, so if our x equals a, so in this case, if we make the denominator 0, we're going to have a vertical asymptote at that point. Okay, so anything that makes this a denominator 0 will make a vertical asymptote. Okay, so in this case, a vertical asymptote would happen at x equals 2. Okay, so we would have a vertical asymptote here. Okay, I'll get into the horizontal asymptotes in a bit, but it will be here at 1. And it's not because that there's a 1 on the top. Okay, I'll explain with the next, I think another example at the bottom. Okay, so we'll have a vertical asymptote here and a horizontal asymptote here. The graph, since it is kind of like a reciprocal function, but it's a rational functions, it could be in the opposite quadrants or in these two here. Just to graph something, I'm just going to put it here for now. Okay, I don't know if that's the answer for this example, but I want to use this example for the asymptotes. Okay, so if we can make the denominator 0, we have the vertical asymptote here. Okay, next one. Okay, so if there's a number that can make both the numerator and denominator 0, then we say there's a hole in the graph. Okay, so a hole, just like we did on number lines, the hole, or when we did piecewise function, when there was the hole in the equation, same idea. Okay, so for instance, I'll give you an example. I think there's examples afterwards. 1 second. Oops, I should have went down there. Okay, so an example of this, and my example here is x squared minus 4 over x minus 2. Okay, so here, is there a number that I could put into the numerator and the denominator that would make the whole thing 0? Okay, so the number that we can plug in here and here that will make it 0 is 2. So if I put 2 in here, 2 squared is 4, minus 4 is 0. And I put here 2 minus 2 is 0. Okay, so there's a number. An easier way to do this one is to factor wherever possible. So factor out the numerator. So x minus 2 and x plus 2. Okay, so this one has a hole. This makes it easier to look at, so we could plug a 0 and 0 into here. okay? So this would end up crossing off. So we end up getting a graph that looks like this. Okay, so the other way to know that it has a hole, not just by looking at it, if you're able to cancel out a numerator and denominator together, there will be a hole at that point. So whatever you could cross off, there's going to be a hole in that position. Okay, so if I factor this, so this was a difference of squares. So I square root x, I get x and x. Square root 4, I get 2 and 2, 1 positive, 1 negative. Then I was able to cross off these because they are like terms. Sorry, we're dividing and multiplying by the same binomial. Okay, so you cross it off, so you're left with, the function is just x plus 2. So you're just left with this. So this becomes a linear equation. So when I graph this, it starts at, your b is 2, and then your slope is 1 over 1, so it goes up 1 over 1, and so on. Except for, there's going to be a hole at this position here, where x is positive 2. Okay? This hole actually tells you that it's both a vertical and horizontal asymptote at the same position. Okay, but we're not going to do that. So right now we're just, when you're able to factor out and cancel, there is a hole at that position. Okay, C. I don't know why this got. Okay, so we're supposed to have a graph. It's at the bottom of the page. Okay, so now we're talking about the horizontal one. So I kind of showed you what the one previously had a horizontal asymptote, but now we're going to go through it. Okay, so the horizontal asymptote only when the degree of p at x is less than or equal to the degree of q at x. Okay, so I'll explain that in a minute. The horizontal asymptote can usually be found by dividing the leading coefficients. Okay, it's always going to be the case for us. Okay, so for instance, in my previous example, I had x minus 1 over x minus 2. So I had x plus 1 and x minus 2. Okay, and then my second example, I had x squared minus 4 over x minus 2. Okay, so the rational function has a horizontal asymptote with the degree of p at x. So the degree here, p at x, is less than or equal to the degree of q at x. Okay, so this is p at x and this is q at x. Okay, so the degree of this is 1, the degree of this is 1. So it is therefore, it is less than or equal to. So in this case, it's equal to. In this second example, ignore that I said before about the horizontal through the hole. It's not the case, it's the vertical in that example. Here now, the degree is 2, and here is the degree is 1. This would not have a horizontal asymptote because the degree is higher here. It's not less than or equal to. Okay, so now, so this one won't have a horizontal asymptote. So now that this one is equal or less than, we can find a horizontal asymptote in this case. And the way you find it is to take the leading coefficients. So the leading coefficient is 1, and the leading coefficient is 1 here. So 1 divided by 1, we're going to have a horizontal asymptote, and x equals 1. Okay, 1 divided by 1 is 1. That's why in the upper, if you go back to the first example, I put a horizontal asymptote at 1. Okay, it's because I divided the fraction. Okay, I'll give you another example. Oh my goodness. my next example is 2x over x plus 1. Okay, so if I were to graph this, I would have a vertical asymptote, so a vertical asymptote at -1, because it will make the denominator 0. So the vertical asymptote at -1. Okay, and then, you guys see that on there? And then what we do is since the degree here is 1, degree here is 1, so that means this one is less than or equal to this one. So we can take the leading coefficients and divide them. So 2, and this would have a 1 here in front of the x in the denominator. So 2 divided by 1 is 2. So my horizontal asymptote is at 2. Okay, and then for our purposes, I'm going to draw this, I don't know, this doesn't matter for now, in this quadrant and this quadrant. Don't worry about where it is at the moment. Okay, right now, this lesson is for you to recognize the vertical asymptotes and horizontal asymptotes. Okay, and our last one. Okay, so a rational function has an oblique asymptote. I'll draw it out for you. So an oblique, which is a slant, oblique asymptote only when the degree of px is greater than the degree of q at x by exactly 1. So if the numerator is greater than the denominator in the degree by 1, then it has an oblique asymptote. In the previous example, I did have a degree that was 1 higher, but I was able to factor it and cross it out. So the top one had x squared minus 4, and the bottom, I'll show you again. Okay, so my example is x squared plus 4 and x plus 1. Okay, so this right now, we have the degree in the numerator is exactly 1 degree higher than the numerator. So this is a 2, this one is a 1. Okay, so this means there's going to be an oblique asymptote. Okay, but before I draw that, I'm going to put my vertical asymptote. My vertical asymptote is at x equals -1. Okay, my vertical asymptote's there, and my oblique asymptote is going to go through. It's going to go through here. You do not need to know, when we do our lessons, how to draw an oblique asymptote. I will not ask you to draw where the oblique asymptote is. You just have to know that the degree is, if it's higher here by 1, only 1, then it does have an oblique asymptote. Okay, and then the graph's going to look kind of funny. It's going to look like this. Okay, I will not ask you to draw one that's like this with an oblique asymptote. Okay. Okay, the last thing I want to correct is the previous. Sorry, in example 2, I put this question as an example. This one did have a degree that was 1 higher than the one in the denominator, but this one was able to be factored and we're able to cross it off. So when we factored it, x minus 2, x plus 2, all over x minus 2, since we could cross off, this one is not going to have an oblique asymptote. This one has a hole. Okay, if this one has a hole, because we could cross off, we could substitute a 0 into both of these. Sorry, plug in a 2 to both of these, and it would make the whole rational function a 0. Okay, this one we cannot factor. Okay, degree is 1 higher than this, so this one's going to have an oblique asymptote. Okay, that is the full lesson. Okay, it's just a quick one. Okay, the homework is here. Page 262, 1, 2, omit J. Omit J because, what was J? It has an example that we're not going through, and then 3, A, B, C, D. Okay, so for the first one, you're matching graphs in the equation together. For number 2, you're identifying any vertical asymptotes, holes, or any horizontal. We're looking at all the asymptotes. Okay, and then 3, you're gonna have to draw something out. Okay, so that is the work for today. Or in this case, it would be for you guys, yeah, today and tomorrow.